All right, welcome to the deep dive. We all want to get smarter, right? But who has time to wade through endless articles and research papers?
Well, that's where we come in. We do the heavy lifting, dig into the fascinating stuff, and bring you those key insights and surprising facts that really make everything click. And we keep it fun.
That's right. Today we're taking a deep dive into a really cool research paper. It's called Magma, a foundation model for multimodal AI agents. And you can find it on arxiv, that's arxiv.org, PDF 2502.13130.
This paper introduces a brand new AI model called Magma. And it's aiming for something pretty ambitious, like a much more integrated way of understanding and interacting with the world than we've seen before.
Think about all the AI applications we have now.
Yeah, like everywhere these days.
Exactly. Well, Magma's aiming for a more, I guess you could say, holistic, a more complete grasp of reality.
Okay, so let's break this down. What makes Magma's approach to AI different? It's all about this idea of multimodal input, which means it can process not just text, but also visual information like images and videos.
And then it can actually act on that understanding, whether it's navigating a website or controlling a robot in the real world.
That's pretty amazing.
So our mission today is to explore what makes Magma tick and what these capabilities could really mean for the future. And we're going to do it without getting lost in all the technical jargon.
Absolutely. To really get why Magma is such a big deal, we need to take a quick look at what's been happening with AI agents. We've seen some serious progress with something called Vision Language Action Models, VLA for short. These AI systems, as the name suggests, can process visual information and language to take action.
VLA, got it.
Right.
So, but here's where things get really interesting. The researchers behind Magma point out this big limitation with a lot of these existing VLA models. They're often trained separately for the digital world, like interacting with websites or apps, and the physical world, like controlling robots.
And that's a problem.
So it's like they're stuck in their own lanes.
Exactly. It's like having a specialized tool that's fantastic at one thing, but useless for anything else. This siloed approach means AI can't apply its knowledge of, say, moving objects in the physical world to navigate a digital map. It's stuck.
So it's limiting their adaptability.
Exactly. And that's a problem Magma solves. Magma's ambition is much bigger, aiming to be a foundation model.
Okay, foundation model, what does that mean exactly?
Well, the idea is to create one fundamental AI model trained on this huge data set that can then be adapted for a whole range of tasks. And this model needs to be able to do two things really well. It needs to have strong multimodal understanding, meaning it can grasp the meaning, the spatial relationships, and how things change over time in both visual and language inputs. And then it needs to be able to predict accurate sequences of actions.
Across all sorts of environments, both digital and physical.
Exactly. It's not just seeing and comprehending, it's acting and doing it in a way that makes sense across different contexts.
Right. It's like connecting the dots between understanding and action.
Yeah. And that leap from understanding to action, especially moving from the abstract world of language to the concrete world of physical actions, is a huge challenge.
I can imagine.
Think about it. We can easily describe an action like click the button, but for an AI to actually do that, it has to first visually identify the button and then translate that understanding into specific coordinates on the screen.
Oh, I see. It's like translating between languages.
Right. Or think about telling a robot to pick up the mushroom. The robot needs to recognize the mushroom and then coordinate the precise movements of its arm to actually pick it up.
Wow, that's a huge gap to bridge.
It is. So how does Magma even start connecting this verbal understanding with spatial actions? That's where these two really cool techniques come in. They're called set of mark or sum and trace of mark or tom.
Set of mark, sum, and trace of mark, tom. Got it. These sound like they're at the heart of Magma's innovation.
They absolutely are.
Yeah.
Let's start with set of mark sum. This is how Magma does what's called action grounding. Imagine a picture, maybe a screenshot of a website.
Okay, got it.
Now, within that image, there are all these things you can interact with. Buttons, links, text fields. So Magma basically involves labeling these actionable visual objects with like little numerical marks or bounding boxes. It's like putting a tag on a button that says, hey, this is something you can interact with.
So like putting a little flag on it.
Exactly. And the paper actually shows some great visual examples in Figure 1. You can see these clickable buttons in a user interface, each with a little number to show it's marked. You also see a picture of a robot arm with different parts of it marked in the same way. And Magma learns to pick out these marked regions when it needs to do something.
Okay, so let's say the instruction is book a hotel. Magma would use these marks to find the search bar, the date selector, and the search button. and then it would know to interact with those specific areas.
Precisely. It's like Magma is grounding its understanding in the visual reality of the interface. It's learning to connect language commands with the actual visual elements it can act on.
So it's not just understanding the words, it's understanding where to apply them.
Right. And this applies not just to clicking buttons on a website, but also to figuring out how to manipulate objects with a robot arm.
That makes sense for single actions in a static image. But what about sequences of actions that happen over time, like in a video? How does Magma handle that? That's where trace of Mark, or Tom, comes in, right?
Exactly. Trace of Mark takes that sum idea and extends it to videos. Instead of just marking objects in a single frame, it actually tracks their movement, the trace, over time.
Oh, I see.
So if we go back to figure 1, we see examples like the trace of a hand peeling a potato, or the path a robotic arm takes when moving an object. It's like drawing a line that follows the important parts of the action as it unfolds.
That's a really clever way to visualize it. So Magma learns to predict these future trajectories.
Exactly. And that's how it starts to plan sequences of actions. By seeing how things move and change over time in videos, it learns to anticipate the consequences of its own actions.
It's like learning to think ahead.
Yes, exactly. And this is much more efficient than trying to predict every single pixel in future video frames. It can focus on the movement of the key elements.
It's like focusing on the essential parts of the story, cutting out all the unnecessary details.
Right. And this means it can handle much longer sequences of actions without getting bogged down.
So Magma is pre-trained using these SOM and TOM techniques on just a huge amount of data. What kinds of data did they use?
It's a really diverse mix. They've got static images, videos of people doing things, data sets that show how people interact with interfaces, and data from robotic manipulation tasks. It's like they gave Magma this incredibly well-rounded education.
It's like going to the ultimate school of experience for AI.
Right, and it's not just the variety, it's the sheer volume. They used about 39 million samples. That's a massive amount of information for a single AI model to learn from.
Wow, 39 million. That's a lot. Okay, so after all that training, they put Magma to the test, and they focused on 3 key areas.
Right, let's dive into those. The first one is UI navigation. Basically, how well does Magma handle getting around and doing things on websites and in apps?
And how'd it do?
It did phenomenally well. Magma actually achieved what we call state-of-the-art results on some really important benchmarks, like Mind2Web and AITW. That means it performed better than any other model out there on these specific tests, which look at how well an AI agent can understand instructions given in natural language and then actually do those things in web and mobile interfaces.
So it's like it aced the test.
Exactly. And what's really impressive is that it even beat out models that were specifically built for these UI tasks, like one called C-Click.
So it wasn't even its main focus, but it still came out on top.
Exactly.
Can you give us some examples of what kinds of things Magma could do in this UI navigation domain?
Sure. It can handle tasks like book a hotel, which means it had to understand the goal, find the right search fields, type in locations and dates, and then click the search button. It could break down these complex instructions into smaller, actionable steps.
That's amazing. Okay, moving on to the real world, the second area is robotic manipulation. How did Magma do when it came to actually controlling robots?
Well, this is even more impressive. Magma got state-of-the-art results in robotic manipulation tasks, too, on benchmarks like SimplerM, Bridge, and Libero. It even beat models that were specifically trained for robotics, like OpenVLA and RT2.
So again, beating the specialists.
I know, right? It suggests that Magma has a much deeper understanding of physics and how to manipulate objects. It's not just memorizing specific actions.
So it's like it's actually learning the underlying principles.
Yeah.
What kinds of robotic actions are we talking about here?
Think about things like close the drawer, pick up the mushroom and put it in the pot, or even something more complex like place the carrot on the plate. Figure 8 in the paper shows just how much better Magma did on these tasks compared to other models which really struggled.
I'm looking at Figure 8 now, and it's pretty clear that Magma is way ahead. And it wasn't just in simulations, right? They actually tested it with real robots.
You got it. Figure 9 shows the results from experiments they did on a real WidowX robotic arm. Magma did amazingly well, things like pick and place a hot dog sausage. And it could even generalize to new tasks it had never seen before, like push the cloth from right to left.
So it was able to adapt on the fly.
Exactly. And it significantly outperformed the OpenVLA model in that task. This really shows that Magma understands the physical actions involved. It's not just memorizing a set of instructions.
Wow, that's a huge step forward. Okay, last but not least, the third area is general multimodal understanding. Did Magma's focus on action prediction come at the expense of just being able to understand images and videos?
Nope, not at all. In
Hmm.
fact, Magma did really well on standard image and video understanding tasks like GQA and Video ME. It was on par with large multimodal models that were trained on much, much larger data sets, and their whole focus was just understanding.
So it's a multi-talented AI, huh? What kinds of multimodal understanding tasks did it excel at?
Well, it could do things like answering questions about what's in an image, figuring out the sequence of events in a video, and tasks that involve spatial reasoning. For example, it showed really strong spatial reasoning abilities on benchmarks like VSR and spatial AVL.
Spatial reasoning, meaning understanding where things are in space and how they relate to each other.
Exactly. And it even outperformed models like CogVLM, even though it used way less training data.
Less data, better results.
Table 6 and Figure 11 in the paper show this really clearly. And here's the kicker. Those SUM-MM and TOM techniques, the ones designed for action grounding and planning, they actually help boost this spatial reasoning ability too.
So it's like learning to act actually helped it understand the world better.
It's fascinating, isn't it? Understanding where things are and how they relate to each other in space is fundamental for both understanding and acting in the world.
That makes a lot of sense.
And Magma also did well on video question answering benchmarks, especially tasks that required understanding how things change over time and predicting future actions. You can see this in Table 8 on benchmarks like Intent QA and the action prediction part of MVBench. It really supports the idea that Tom is teaching the model to think about things unfolding over time.
To think ahead, basically. Okay, so we've covered a lot of ground here. Let's sum it up for our listeners. What are the key takeaways from this deep dive into Magma?
I'd say the biggest takeaway is that Magma represents a huge leap forward in creating AI agents that are both versatile and capable. It's not just about understanding or just about acting. It's about bringing those two things together in a way that works seamlessly across different environments.
And it's all thanks to these really innovative techniques, SOM and Tom. They provide this incredibly effective way to teach AI models not just to see the world, but to actually interact with it and understand how actions play out over time.
Precisely. And Magma shows us that we might be able to create a single AI model that can achieve really high levels of performance in both the digital and the physical realms. That's something that's been really hard to do with previous models.
And the results really highlight how important spatial and temporal understanding is for building AI that can function effectively in the real world. It's not just about recognizing objects, it's about understanding how they're arranged and how they change over time.
And here's one last fascinating tidbit from the paper. Even though Magma wasn't specifically trained on data about mazes, it could still answer spatial reasoning questions about them. You can see this in Figure 11.
So it was able to apply its knowledge to something completely new.
Exactly. And that hints at a level of generalization and abstract reasoning that is incredibly promising.
That's really exciting. So to recap, this deep dive into Magma has shown us a new foundation model that's really shaking things up in the world of multimodal AI. It has a strong grasp of different kinds of input. It performs amazingly well in both UI navigation and robotic manipulation. And it shows some really impressive spatial and temporal reasoning skills.
All thanks to those novel SOM and TOM techniques. It's not just passively observing, it's actively learning to interact with and understand the dynamics of the digital and physical world in a much more unified way.
Now, here's a final thought for our listeners to ponder. Given Magma's ability to connect understanding and action across these different environments, what future applications could this kind of versatile AI enable in your own field or areas of interest? And what are the broader implications as AI becomes more and more capable of interacting with both the digital and the physical world around us?
Those are really crucial questions to think about as this technology continues to evolve. We encourage you to check out the full research paper. You'll find the link in the show notes.
It's definitely worth a read.
It is. And take some time to think about the incredible potential, but also the broader implications of these kinds of advancements.
And that brings us to the end of this deep dive. We hope you've enjoyed this exploration of the Magma model.
We've only just scratched the surface, really. There's so much more to discover.
That's true. Stay tuned for our future deep dives into more cutting-edge research that's shaping the world around us.
We'll be back soon with more exciting discoveries.
See you then. Bye.